Hello, my friend, and welcome. Tonight, we're drifting into the science of time, from the clocks in your mind to the age of the universe itself. So get comfortable, relax, and let this journey through time slowly carry you to sleep. Chapter 1. What time feels like. Time does not arrive in the human mind as a clock face. It does not appear with markings, units, or a neat universal rhythm. What we actually experience is something much softer and stranger. We feel duration, we feel waiting, we feel anticipation, boredom, urgency, relief, routine, and change. In daily life, time seems to speed up, slow down, stretch, compress, and sometimes disappear almost completely. This is one of the first important scientific truths about time. The time we live through is not identical to the time that physics measures. It is a constructed experience shaped by the brain, the body, attention, memory, and the rhythms of life itself. That may sound surprising at first, because clocks feel so objective. A minute is a minute whether you are happy, anxious, exhausted, or in love. But human beings do not experience minutes in a perfectly clock-like way. In psychology and neuroscience, subjective time refers to the felt passage of time rather than the measured passage of time. Those two can drift apart. When you are deeply engaged in something absorbing, time may seem to pass quickly. When you are uncomfortable, uncertain, or watching for something to happen, the same amount of measured time can feel much longer. Research in time perception shows that judgments of duration are influenced by attention, perceptual richness, emotion, and memory. In other words, time as felt by the mind is elastic. Part of the reason is simple. The brain does not seem to contain a single little clock that ticks in one place for every purpose. Instead, timing in the brain appears to arise from distributed processes. Different scales of time, from fractions of a second to the daily sleep-wake cycle, involve different mechanisms and different networks. Neuroscientists have long argued that temporal experience is woven out of perception, action, internal bodily states, and memory rather than produced by one central dial. So when we ask what time feels like, we are really asking how the brain organizes change. Consider the feeling of waiting. If you are standing in line with nothing to do, your attention often turns toward the passage of time itself. You notice each small delay. You monitor the environment. You keep checking whether anything has changed. That act of monitoring can make a short interval feel longer. But if your attention is captured by conversation, music, reading, or a task that fully occupies the mind, the same interval can feel shorter because fewer mental resources are spent tracking duration. One major idea in time perception research is that attention changes how duration is experienced. Time often feels longer when it becomes the object of attention and shorter when attention is directed elsewhere. Emotion changes it too. Strong feelings can alter the experience of passing time in powerful ways. Fear, tension, and uncertainty often make moments feel drawn out. People frequently report that frightening events seem to unfold in slow motion. That does not necessarily mean the brain suddenly becomes a perfect high-speed recorder. More often, it means that arousal and attention reshape the experience of the event and the memory left behind by it. Positive states can distort time as well, though not always in the same direction. The familiar phrase that time flies when you are having fun captures a common pattern. But scientific studies show something more nuanced. Emotional valence, arousal, and motivational state all matter. Time perception is not ruled by one simple law of feeling. Memory is another quiet architect of time. There is an important difference between how long an experience feels while it is happening and how long it seems when we look back on it later. A routine week may feel busy in the moment, yet blur together in memory. A novel trip may pass quickly while you are living it, but later seem long and full because it contains so many distinct memories. This helps explain why periods of life filled with repetition can seem to vanish in retrospect, while periods of change and first experiences seem larger and more spacious when remembered. Subjective time is not only about what the mind senses now. It is also about how the mind stores what happened. This is one reason childhood can appear so long when remembered from adulthood. Early life contains many firsts, new places, new skills, new emotions, new social worlds. Because the brain is building so many fresh models of the world, those years are dense with memorable structure. Later, when life becomes more familiar and patterned, fewer moments stand out. The clock has not changed, but memory has changed the apparent size of whole stretches of life. Scientists continue to debate the details, but the broad principle is well supported. Novelty, attention, and memory density strongly influence retrospective time. The body also contributes to temporal experience. We do not merely think time. We live it through rhythms. Heartbeat, breathing, fatigue, hunger, hormone cycles, light exposure, and sleep pressure all help organize the sense of when things should happen and how long a day feels. Human beings possess circadian rhythms, near daily cycles that regulate sleepiness, alertness, body temperature, hormone release, and many other processes. These rhythms are strongly influenced by light and coordinated by biological clocks in the brain and throughout the body. When those rhythms are disrupted through jet lag, night work, poor sleep, or irregular schedules, people often report that time feels strange, flattened, or out of sync. This is important because it shows that our feeling of time is not purely abstract. It is physiological. Morning does not feel like evening, even in the same room. A sleepless night changes the weight of hours. A long day under artificial light can loosen the familiar structure that sunrise and darkness normally provide. Scientists studying circadian systems have shown that light is a major cue for biological timing, and that attention, mood, and performance fluctuate across the day as part of these rhythms. So the felt texture of time is partly shaped by where the body is within its daily cycle. At smaller scales, the brain also has to solve an extraordinary problem. It must bind events together across tiny windows of time to create a smooth present. Sounds arrive in sequence. Light reaches the eyes in changing patterns. The body moves through space. Yet consciousness does not usually feel like a chaotic stream of fragments. It feels continuous. The nervous system appears to integrate information over short intervals, creating a workable present moment rather than exposing us to raw, disconnected instants. Researchers still debate exactly how this works, but the basic point is clear. The present as we experience it is already a biological construction. The brain is constantly predicting, comparing, updating, and stitching. It uses the recent past to interpret the present and to anticipate what comes next. In this sense, lived time is closely related to expectation. If nothing changes when change is expected, time can seem to drag. If many things change at once, time can seem full and vivid. If the mind settles into a stable rhythm, hours may drift by almost invisibly. Time, as felt, is deeply entangled with change detected and change anticipated. Music offers a beautiful example. Rhythm gives the mind a patterned form of time. Beats allow expectation to form, and the body often responds automatically. Research on rhythm perception suggests that timing is linked not only to hearing, but also to motor systems and bodily coordination. We do not passively receive rhythm, we participate in it. The same is true in everyday life. Walking, speaking, eating, working, and resting all involve timing, and much of that timing is embodied. Our sense of duration is partly a sense of movement through structured patterns. There is also a deeper psychological point. Human beings do not simply experience isolated moments. We experience temporal direction. We remember the past, attend to the present, and imagine the future. Memory and anticipation give time its emotional tone. Regret belongs to what has happened. Hope belongs to what might happen. Anxiety often pulls awareness forward, while nostalgia pulls it backward. This means the feeling of time is not only sensory or biological, it is also personal. To feel time is to feel oneself moving through a world of becoming. And yet, for all its distortions, subjective time is not a flaw. It is useful. A perfectly rigid internal experience of time might be less adaptive, not more. The flexibility of temporal experience helps the mind prioritize what matters. Danger can feel expanded. Repetition can be compressed. Novelty can leave a large imprint. Attention can redistribute mental resources depending on need. What feels like inconsistency may actually reflect a highly responsive system shaped by evolution to track relevance, not merely duration. So when people say that time seemed to disappear or that a day lasted forever, they are not merely speaking poetically. They are reporting something real about the way the mind constructs temporal life. Physics gives us measured intervals. Biology gives us rhythms. Psychology gives us duration as lived. Memory gives us the size of the past. Together, these create the world of felt time, the world each of us actually inhabits from morning to night. And perhaps that is a gentle place to begin any journey into the science of time. Before time becomes relativity, entropy, or cosmology, it first arrives as an experience, a quiet sense that moments open, pass, and settle into memory. Tonight, there is no need to hold on to every minute or measure the day any further. You can let time move on without asking anything more from you, and simply rest inside its slow and steady flow. Chapter 2. How Humans Learn to Measure Time. Long before human beings could measure time with precision, they were already living inside patterns that demanded attention. Day followed night. The moon changed shape. The seasons returned in cycles that governed warmth, cold, rain, migration, planting, and harvest. The first timekeeping was not mechanical at all. It was observational. People learned to notice repeating changes in the sky and on the land, and from those changes they built the earliest practical understanding of duration. In that sense, the science of timekeeping began not with clocks, but with careful watching. The most obvious rhythm was the alternation of light and darkness caused by Earth's rotation. That rhythm created the day, the most immediate natural unit of time available to any society. But a day alone was not enough. Human communities also needed longer patterns. The changing appearance of the moon provided one of the earliest visible cycles that could be tracked across many nights, and the yearly motion of Earth around the sun revealed itself through shifting seasons and the changing height of the sun in the sky. These repeating astronomical patterns made it possible to divide time into days, months, and years, long before anyone understood the deeper physics behind them. Early calendars emerged from this need to organize communal life. Agriculture, religious ceremonies, taxation, travel, and political authority all benefited from a shared agreement about when things should happen. Many early cultures used lunar or lunisolar systems because the moon's cycle was easy to observe. Yet, lunar months alone do not stay aligned with the solar year and the seasons. That mismatch created a major challenge. If a society wanted months to remain connected to seasonal life, it had to insert corrections. This is one of the great scientific lessons of calendar history. Measuring time is not just about counting repeated events, but about reconciling several natural cycles that do not fit together perfectly. The ancient Egyptians developed a calendar strongly tied to the solar year, which was especially useful for agriculture along the Nile. Other civilizations refined lunisolar systems with intercalations, adding extra time when needed to prevent the calendar from drifting away from the seasons. These were not crude guesses. They were early forms of astronomical problem-solving. Priests, scholars, and officials observed the sky, compared records across years, and tried to align human order with celestial regularity. The calendar was therefore more than a schedule. It was a scientific instrument for society. If calendars solved the problem of long time, the day created a different one. People needed ways to divide daylight into smaller parts. One of the earliest tools for this was the sundial. Its principle is wonderfully simple. As the sun appears to move across the sky, the shadow cast by an object changes length and direction. By marking those changes, a person can estimate the time of day. Sundials were elegant because they turned Earth's rotation into something visible on the ground. But they also had obvious limits. They depend on sunlight, they vary with location and season, and they cannot function at night or under heavy cloud. Even so, they represented a major step because they transformed the broad passage of a day into readable intervals. To measure time when the sun could not help, people developed water clocks and other flow-based devices. A water clock uses the regular movement of water, either flowing into or out of a vessel, as an indicator of elapsed time. These devices appear in several ancient cultures and became increasingly sophisticated. Some later versions regulated flow more carefully and even powered displays, bells, or moving figures. What matters scientifically is the shift in principle. A sundial measures time by referencing astronomical motion directly. A water clock measures time by using a controlled process on Earth as a proxy. That idea would become essential for the future of clocks. If a process is regular enough, it can stand in for time. The search for regularity led eventually to mechanical clocks. In medieval Europe, the first truly mechanical clocks used systems of gears and escapements to control motion and divide it into repeated steps. These clocks were not immediately precise by modern standards, but they changed civilization profoundly. For the first time, large communities could hear and obey the same hourly signal from towers and public buildings. Timekeeping was becoming detached from direct observation of the sky and embedded into built environments. Towns could coordinate labor, prayer, commerce, and civic life in a more uniform way. The clock did not merely measure time. It reshaped social behavior around measured intervals. The key technical advance in these clocks was controlled repetition. The escapement released motion in a series of regulated steps, preventing weights or springs from unwinding all at once. This was an enormous conceptual achievement. Instead of letting motion run freely, clockmakers forced it into countable beats. Yet early mechanical clocks still drifted significantly. They were useful for shared coordination, but not for fine science or navigation. Precision required something more stable than a simple gear train. That next leap came with oscillation. A swinging pendulum has a remarkably regular period under suitable conditions, and in the early modern period, pendulum clocks dramatically improved accuracy. Later, spring-driven clocks and balance wheels made portable timekeeping more practical. Each improvement reflected the same scientific ambition: find a physical process whose repetition is as uniform as possible. The history of timekeeping is therefore also a history of identifying better oscillators. A clock becomes better when its repeated motion becomes less sensitive to friction, temperature, position, and environmental disturbance. This growing precision mattered for more than convenience. It became vital for astronomy, surveying, and especially navigation. Determining longitude at sea depends on comparing local time to the time at a known reference location. That requirement turned accurate portable clocks into instruments of global importance. Timekeeping and geographic knowledge became deeply linked. A ship carrying a good clock was carrying not just a device, but a way of locating itself on Earth. This was one of the moments when measuring time became inseparable from measuring space. As societies industrialized, timekeeping grew more standardized and more pervasive. Public clocks, railway schedules, factory hours, and later telegraph signals demanded common time across larger territories. Local solar time, once sufficient for many communities, became increasingly inconvenient when transport and communication accelerated. Standard time zones were part of the solution. They reduced the chaos that would arise if every town kept its own noon based strictly on the sun. In this phase, time measurement became a networked social system, not just a local observation or a private device. Then came the modern revolution. The realization that atoms provide even more stable regularity than pendulums or quartz oscillators. Atomic clocks do not rely on the motion of gears or the swing of a mechanical object. They rely on highly regular transitions associated with atoms, especially cesium in the modern definition of the second. This was a turning point because it anchored timekeeping to properties of nature that are extraordinarily reproducible. Instead of building better machines alone, scientists began using fundamental physical behavior as the basis of time standards. The modern second is defined through the cesium atom, and international timekeeping now depends on ensembles of atomic clocks maintained by laboratories around the world. These clocks are compared and combined to create international atomic time, while coordinated universal time serves as the civil standard used globally. Because Earth's rotation is not perfectly uniform, civil time must still remain related to the planet's actual orientation, which is why the story of timekeeping has not fully escaped astronomy. In the modern system, atomic regularity and Earth's uneven rotation have to be reconciled. This is a sophisticated continuation of an ancient problem. Human beings still have to match their timescales to multiple natural realities at once. What changed across all these centuries was not only precision, but also the meaning of time measurement. At first, people read time from the world around them. Then they built devices that imitated regularity. Eventually, they discovered that nature itself contains levels of regularity far beyond ordinary perception. The path from shadows to water, from gears to pendulums, from quartz to atoms, is really a path toward ever finer ways of comparing change against change. Every clock answers the same question in a different language. What process can we trust to repeat? And yet, the deeper story is not simply one of increasing control. Human beings did not invent time itself. They invented methods for aligning their lives with recurring structures in nature. The day was there before any dial. The year was there before any calendar. The atom was oscillating long before any laboratory counted it. What changed was our ability to notice, compare, and agree. Timekeeping became more accurate as our understanding of nature became more exact, but it always remained a dialogue between human need and cosmic order. There's something quietly humbling in that history. Across thousands of years, from watching the moon to averaging atomic clocks across continents, human beings kept refining the same effort to place themselves within patterns larger than themselves. A calendar is a social tool, but it is also a confession that we live by cycles we did not create. A clock is a machine, but it is also a reminder that our days can be compared against motions far more stable than our own. We learn to measure time because we are temporary creatures trying to orient ourselves inside a universe that keeps moving, whether we understand it or not. And perhaps that is why timekeeping feels larger than technology alone. Every better clock has been, in its own way, an attempt to listen more carefully to reality. The more precisely we measured the world, the more clearly we discovered that we were never standing outside time at all. We were always inside it, learning slowly, century by century, how to hear its rhythm. Chapter 3. What time is in classical physics? When classical physics began to take shape, time was treated not as something mysterious, flexible, or dependent on the observer, but as something steady, universal, and quietly reliable. In that framework, time was the background against which all motion unfolded. Bodies moved, forces acted, planets orbited, pendulums swung, and projectiles rose and fell, but time itself did not participate in these events. It did not bend, slow, or vary from place to place. It flowed evenly everywhere. This idea became one of the deepest foundations of Newtonian physics and of the wider classical worldview that followed from it. This was an extraordinarily powerful way to describe nature. If time passes identically for everyone, then events can be arranged along a single common timeline. One moment happens before another, and the duration between them is the same for all observers, no matter where they are or how they move, so long as the ordinary assumptions of classical mechanics are being used. In this picture, the universe resembles a vast stage on which matter changes position with time, while time itself remains untouched by those changes. Space provides the arena of positions, and time provides the arena of succession. Together, they form the stable setting for mechanics. Isaac Newton gave this idea its most influential expression. In his account, absolute time exists independently of the events that occur within it. It does not depend on clocks, on the motions of celestial bodies, or on human perception. Clocks are merely devices that try to track time. They may succeed well or poorly, but time itself is not created by them. This distinction mattered deeply in classical physics. Measured time could be imperfect, but true time was assumed to flow equably on its own. That belief allowed physicists to describe motion mathematically as a change of position with respect to a uniform time parameter that was the same everywhere. Once that assumption is in place, the laws of motion become far easier to formulate. A body continues in its state of rest or uniform motion unless acted upon by a force. Forces change motion in lawful ways. A planet accelerates toward the sun, a stone falls toward Earth, and a cart speeds up when pushed. All of this can be described because time is treated as the common measure of change. Without a shared time variable, the clean structure of classical mechanics would be much harder to express. In Newtonian physics, one does not ask whether time itself might behave differently for different observers. One assumes that it does not. This assumption fit ordinary experience remarkably well. In everyday life, clocks agree closely enough for practical purposes. If two people stand in different places in a town, they do not notice any meaningful difference in how quickly time passes for them. If a carriage moves down a road, its motion can be described using the same shared time that applies to someone standing still nearby. The success of classical mechanics in describing falling bodies, machines, tides, planetary motion, and engineering problems made absolute time feel not only convenient but natural. It seemed to match the world. Classical physics therefore treated time as continuous and uniform. Continuous means that time is not made of separate jumps in the classical picture. It can be divided conceptually into smaller and smaller intervals without encountering an inherent grain. Uniform means that equal intervals of time are equal everywhere and always. A second today and a second tomorrow are assumed to be the same in principle. This regularity was crucial because it made nature look lawful. If time itself were unstable, then the comparison of motions across different situations would become uncertain. But if time flows evenly, then regularities in motion can be discovered, tested, and generalized. There was also an intimate connection between classical time and prediction. Classical mechanics became famous for its deterministic character. If the positions and velocities of bodies are known at one moment, and if the forces are known, then in principle their future motion can be calculated. One can also calculate the past. This way of thinking depends on time being a stable coordinate through which systems evolve. Classical time is not only the measure of change, it is the axis along which prediction and retrodiction become possible. It allows nature to appear orderly enough that the future unfolds from the present according to precise laws. This does not mean that all classical thinkers agreed about every philosophical detail. Even in Newton's own era, there were debates about whether time truly exists independently or whether it is only a way of describing relations among events. Leibniz, for example, objected to the idea of absolute space and time and argued for a more relational view. Later thinkers continued to question whether absolute time was something real in nature or simply a useful structure in theory. But within the working practice of classical mechanics, the Newtonian picture proved so successful that it dominated physics for centuries. The debate did not prevent the equations from working. Another important feature of classical time is that it is external to the system being studied. If one analyzes a pendulum, a cannonball, or a planet, the time variable is not usually considered part of the mechanism itself. It is the independent parameter against which the system's changing state is measured. This is one of the reasons classical physics feels so clear and intuitive. The world is described as things moving in space as time passes, rather than space and time being dynamically involved in the physical process. Time in classical mechanics is therefore more like a perfectly steady ruler for duration than an active participant in reality. This view shaped not just mechanics but much of the scientific imagination. It encouraged the image of a clockwork universe, a world governed by precise laws unfolding on an unchanging temporal backdrop. Celestial mechanics became a triumph of this picture. The same framework that explained the fall of an apple could, in principle, explain the motion of the moon and the planets. That unity was one of the great achievements of classical physics. Time helped make that unity possible because it was assumed to be universal. The Earth, the moon, and the stars all evolved through the same flowing time. It is also worth noticing that classical time was deeply linked to idealization. Real clocks are affected by friction, temperature, imperfection, and environment. But classical mechanics often assumes an ideal clock that marks equal intervals flawlessly. In this respect, time in classical physics is partly an abstraction. It is not merely what any particular clock says. It is what a perfect clock would say if it could track the uniform passage of absolute time without error. This distinction between actual measurement and ideal quantity runs through much of classical science. Nature is described through exact concepts, while instruments strive to approximate them. Classical physics also treated simultaneity as unproblematic. If two events occur at the same time, then they are simply simultaneous in the ordinary, absolute sense. There is no deeper question about whether another observer moving differently might disagree in a fundamental way. In Newtonian thinking, they should not. Different observers may describe motion relative to different frames, but the underlying time remains shared. This is why the classical transformation between moving frames preserves time unchanged. People may disagree about position and velocity, but not about the temporal order or common duration of events in the basic Newtonian framework. That said, classical physics did recognize the importance of reference frames for motion. Velocity is measured relative to a frame, and uniform motion cannot always be identified in an absolute way from within a closed system. But this relativity of motion in the Galilean sense did not yet extend to time itself. Observers in uniformly moving frames still shared the same absolute time. This is an important distinction. Classical mechanics already knew that motion could be relative, but it still held time fixed beneath that relativity. The later revolution of Einstein would not consist in inventing relativity from nothing, but in pushing it further into the structure of time as well. Within its proper domain, classical time remains immensely useful. Much of engineering, everyday mechanics, and astronomy at moderate precision can still be described using Newtonian time with excellent accuracy. Bridges do not require general relativity to stand. A baseball does not require space-time curvature to be caught. Many familiar systems are slow enough and weak enough in gravitational terms that classical assumptions work beautifully. This is one reason Newtonian time remained so persuasive for so long. It succeeds across a vast range of ordinary human experience. Still, even within classical physics, there was something slightly ideal and philosophical about the notion of absolute time. Nobody could point directly to time itself in isolation. One could point to clocks, rotations, oscillations, or orbits, but not to pure time detached from processes. Newton believed the distinction was necessary for mechanics, yet critics asked whether such an unseen and universal time was physically meaningful or metaphysically excessive. That question lingered quietly in the foundations of physics until later developments made it impossible to ignore. In that sense, classical time was both powerful and provisional, strong enough to organize centuries of science, yet not beyond challenge. What classical physics achieved was extraordinary. It gave time a stable role in the mathematical description of nature and allowed scientists to connect terrestrial events with celestial motions under one coherent framework. It taught that change could be measured, predicted, and understood through laws that hold across the world. But it did so by asking us to imagine time as calm, even, and detached from the drama unfolding within it. Time, in that picture, does not age with the universe. It does not feel the weight of matter. It simply passes, identical to itself, everywhere. There is something quietly haunting in that old vision. If classical physics is right within the scale of ordinary life, then much of our existence unfolds against a background that never pauses for us and never changes its rhythm to match our joys or losses. We move, struggle, build, and disappear, while time in the classical sense remains perfectly indifferent. And yet there is comfort in that too. The same steady flow that carried ancient planets and falling rain also carries us, briefly and gently, through our own small portion of the world. Chapter 4: Einstein and the End of Absolute Time. For centuries, classical physics treated time as something universal. It flowed evenly, silently, and identically for everyone, no matter where they were or how they moved. That picture was deeply intuitive, and for ordinary life it worked extremely well. But at the beginning of the 20th century, Albert Einstein showed that this seemingly obvious idea could not survive once the laws of electricity, magnetism, and light were taken fully seriously. The result was one of the most profound changes in the history of science. Time was no longer the same for all observers. It became bound up with motion, with measurement, and with the structure of the physical world itself. The problem did not begin as an attempt to make time mysterious. It began with a conflict between classical intuitions and the behavior of light. In the 19th century, Maxwell's equations had unified electricity and magnetism, and implied that electromagnetic waves travel at a definite speed in empty space. Physicists initially hoped to fit this result into the older framework by imagining a medium filling space, often called the ether, through which light would propagate. If that were true, then motion through this medium should in principle be detectable. But experiments, most famously the Michelson-Morley experiment, failed to reveal the expected effect. Einstein's decisive move was not to rescue the old picture with increasingly complicated adjustments, but to rethink the assumptions underneath it. In his special theory of relativity, Einstein started from two principles. The first was that the laws of physics should have the same form in all inertial frames, meaning frames moving at constant velocity relative to one another. The second was that light in empty space has the same speed for all inertial observers, regardless of the motion of the source. Taken together, these principles lead to consequences that are deeply counterintuitive if one has grown up inside the classical view. They imply that observers in relative motion cannot all share the same universal time. To preserve the observed constancy of the speed of light, measurements of duration and distance must depend on the state of motion of the observer. One of Einstein's most important insights concerned simultaneity. In classical physics, if two events happen at the same time, then they are simply simultaneous for everyone. Einstein showed that this assumption is not physically innocent. To say that two distant events occur at the same time, one needs a method for synchronizing clocks at different locations. Einstein analyzed this problem using light signals and pointed out that such synchronization involves conventions grounded in the behavior of light. Once one accepts the constancy of light speed, it follows that events judged simultaneous in one inertial frame need not be simultaneous in another moving relative to it. In other words, simultaneity is not absolute. That idea alone was enough to break the old concept of universal time. A famous way to picture this is the train thought experiment. Imagine lightning striking both ends of a train. An observer standing on the embankment midway between the strike points may judge the flashes to arrive together and conclude that the strikes were simultaneous. But an observer moving with the train may be traveling toward one flash and away from the other. Because light has the same speed for both observers, the observer on the train may receive the flashes at different times, and therefore conclude that the strikes were not simultaneous. Neither observer is making a mistake. They are applying the laws of physics consistently within different inertial frames. What changes is not the quality of their eyesight, but the structure of time itself. Once simultaneity becomes relative, time itself can no longer remain universal. This leads directly to time dilation. A moving clock, as judged from a frame in which it is moving, runs more slowly than a clock at rest in that frame. This is not a defect in the clock. It is not caused by friction, damage, or bad engineering. It is built into the geometry of space-time in special relativity. Every process that can function as a clock, whether mechanical, biological, or atomic, is subject to the same effect. Relativity does not say that clocks merely appear to behave this way, while secretly sharing a hidden universal time. It says that elapsed time genuinely depends on the path taken through space-time. The light clock thought experiment helps make this more intuitive. Imagine a clock that measures time by bouncing a pulse of light between two mirrors. For an observer at rest relative to the clock, the light moves straight up and down. For an observer who sees the clock moving sideways, the light follows a longer diagonal path between bounces. Since both observers agree on the speed of light, the observer who sees the longer path must also conclude that more time passes between ticks. This is not just a clever visual trick. It captures the logic of the theory. If the speed of light is fixed, then space and time must adjust together. There is a corresponding effect for length. Objects moving relative to an observer are measured to be shortened in the direction of motion. This is often called length contraction. Together, time dilation, length contraction, and the relativity of simultaneity form a unified package. They are not separate oddities added onto the theory afterward. They arise from the same underlying structure. The old separation between space and time begins to dissolve. Distances and durations are no longer fixed independently. They depend on how the observer is moving. This new framework led Hermann Minkowski to formulate space-time as a four-dimensional structure in which space and time are not fully separate arenas, but interconnected aspects of one geometry. In that description, what different observers disagree about is how to divide space-time into space and time. They do not disagree about everything. The space-time interval between events has an invariant status, even while measured lengths and durations vary from frame to frame. This was a major conceptual shift. Einstein had not merely changed some clock readings, he had changed the stage on which physics is written. Special relativity also changed the meaning of the present. In ordinary language, it feels as though the universe possesses one global now, one shared slice of existence unfolding together. But relativity undermines that intuition. Since distant simultaneity depends on the frame of reference, there is no single observer independent present spanning the universe in the old absolute sense. Different observers, moving differently, sort distant events into present, past, and future in different ways. Locally, time still feels ordered. We still remember the past and not the future. But the idea of one universal cosmic now no longer belongs to the deep structure of physics. What made all of this so powerful was not only that it was conceptually elegant, but that it was empirically testable. Time dilation has been confirmed in multiple ways. Fast-moving unstable particles live longer than they would at rest, just as special relativity predicts. Highly precise clocks flown on aircraft or carried by satellites do not remain perfectly synchronized with clocks on Earth unless relativistic effects are taken into account. The global positioning system would accumulate large errors if engineers ignored relativity. In that sense, Einstein's revision of time is not just philosophy written in mathematical form. It is built into technologies that people use every day. It is important to see what special relativity does and does not say. It does not mean that everything is arbitrary or that truth depends on personal opinion. The theory is highly constrained and mathematically exact. Different observers may disagree about durations or simultaneity, but they do so according to precise transformation rules. Nor does relativity make time unreal. On the contrary, it gives time a more carefully defined physical role. The old absolute time was easier to imagine, but Einstein replaced it with something more tightly connected to measurement, causality, and the behavior of light. Another key point is that special relativity applies to inertial frames, frames moving at constant velocity relative to one another. It does not yet include gravity in its full form. That further step would come with general relativity, where space-time becomes dynamic and gravity affects the rate of clocks. But even before that later development, special relativity had already ended the classical dream of a universal time flowing the same way for all. It had shown that time depends on motion, and that the measurement of time is inseparable from the physical conditions under which it is measured. What Einstein destroyed was not time itself, but certainty about its simplicity. He took something that had seemed obvious for generations and showed that it was only approximately true in the slow, familiar world of ordinary experience. Beneath that approximation was a stranger order, one in which clocks carried their own histories, simultaneity dissolved across distance, and the universe no longer offered a single shared tempo to all who moved within it. There is something deeply unsettling in that discovery, but also something beautiful. The world turned out to be less centered on human intuition than we had hoped, yet more coherent than intuition alone could ever reveal. We do not drift through one universal river of time together in quite the way we once imagined. Each path through the universe carries its own measure of duration, and somehow, within that vast and shifting structure, our brief lives still find moments to meet. Chapter 5. Why Gravity Changes Time. By the time Einstein completed special relativity, time had already lost its old classical certainty. It no longer flowed identically for every observer in motion, but an even deeper change was still to come. In special relativity, gravity had not yet entered the picture in its full form. Time depended on motion, but gravity remained outside the theory. Einstein's next step was to ask a more radical question. What if gravity itself changes the rate at which time passes? The answer became one of the central insights of general relativity. Clocks do not all tick at the same rate in different gravitational conditions. The stronger the gravitational field, the more slowly time passes. The path to this idea began with what Einstein called the equivalence principle. He realized that there is a profound connection between gravity and acceleration. A person inside a closed elevator far from any planet, if the elevator is accelerating upward, would feel pressed to the floor in a way that resembles the feeling of weight in a gravitational field. Likewise, a person in free fall under gravity would briefly feel weightless. Einstein took this resemblance seriously. He proposed that, locally, the effects of gravity and acceleration are equivalent in a precise physical sense. This became the conceptual bridge that led him from special relativity toward a new theory of gravity. Once that principle is accepted, the effect of gravity on time begins to emerge almost unavoidably. Imagine light traveling upward inside an accelerating elevator. By the time the light reaches a receiver higher up, the receiver has gained some speed relative to the place where the light was emitted. In the language of relativity, the frequency of the light shifts. If acceleration and gravity are locally equivalent, then light climbing upward in a gravitational field should also change frequency. This effect is called gravitational redshift. Light moving upward away from a massive body is shifted to lower frequency. Light moving downward is shifted to higher frequency, but frequency is deeply tied to time, because the frequency of light can be understood as a kind of oscillation counted by clocks. If light shifts this way in gravity, then clocks at different heights in a gravitational field cannot be running at the same rate. This is the key idea behind gravitational time dilation. A clock closer to a massive object runs more slowly than a clock farther away. Near Earth, the effect is tiny but real. Near a neutron star or black hole, it becomes dramatic. Importantly, this is not a matter of clocks being mechanically damaged by pressure or heat. It is not a side effect of poor construction. It is a property of space-time itself. General relativity describes gravity not as a force pulling objects through an otherwise passive stage, but as the curvature of space-time caused by mass and energy. Clocks trace paths through that curved space-time, and the amount of time they register depends on where they are and how they move within it. In the older Newtonian picture, gravity acted across space while time remained untouched in the background. General relativity replaced that picture with something far richer. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. Time is no longer separate from the gravitational structure of the universe. It is part of that structure. This means that to ask how fast time passes is not to ask for one universal answer. It is to ask where the clock is, how it is moving, and what gravitational environment it inhabits. One of the most elegant consequences of this idea is that gravity affects all clocks in the same way. A pendulum clock, a quartz clock, an atomic clock, a heartbeat, a chemical process, or the decay of an unstable particle all respond to the gravitational environment through the rate at which time itself is experienced along their path. In that sense, Gravity does not selectively interfere with particular devices. It reaches beneath the mechanism and alters the very interval that the mechanism is measuring. This universality is one reason gravitational time dilation is such a profound result. It is not about a special kind of clock. It is about time in the physical world. For a while, this effect remained more of a theoretical insight than a directly measured phenomenon, because near Earth, the difference is extremely small. But over time, experiments confirmed it. One of the classic early demonstrations was the Pound-Rebka experiment, which measured the gravitational redshift of gamma rays traveling in Earth's gravitational field. The results supported Einstein's prediction that light changes frequency as it moves upward and downward in gravity. Later, more precise tests strengthened the case. The effect moved from theoretical speculation to experimental fact. As clock technology improved, physicists were able to test gravitational time dilation much more directly. Highly precise atomic clocks placed at different heights do not remain synchronized. The clock at the higher elevation runs slightly faster than the clock lower down because it is farther from the center of Earth and therefore in a slightly weaker gravitational field. This is not just a cosmic curiosity relevant only to black holes and deep space. It happens across ordinary height differences on Earth. Modern precision clocks are so sensitive that relativistic effects can be measured across surprisingly small vertical separations. This may sound almost unbelievable at first. The clock upstairs and the clock downstairs are not living through time at exactly the same rate. The difference is tiny, far too small for human senses to notice directly, but nature does not require notice in order to be true. The clocks disagree because the structure of space-time differs slightly between the two locations. The universe is not offering one perfectly uniform tempo, even across the surface of a planet. It is offering locally defined durations shaped by gravity. A particularly important real-world example is the Global Positioning System. GPS satellites carry accurate atomic clocks, and their operation depends on accounting for both special relativistic and general relativistic effects. Because the satellites are moving quickly relative to Earth, special relativity tends to make their clocks run slow compared with clocks on the ground. But because they are much farther from Earth's center, and therefore in a weaker gravitational field, general relativity tends to make their clocks run fast. The gravitational effect is larger than the motional one, so the net result is that the satellite clocks would drift ahead if no relativistic corrections were applied. Without those corrections, GPS would rapidly become inaccurate. This means that gravitational time dilation is not merely a theoretical chapter in physics. It is part of the engineering that quietly supports navigation and timing in modern life. Gravity's influence on time also helps explain why light escaping from very massive objects becomes redshifted. If a clock deep in a gravitational field runs slowly, then any periodic process associated with that clock will also appear slowed when observed from farther away. Light emitted there will arrive stretched toward lower frequency. In this way, gravitational redshift and gravitational time dilation are two closely related perspectives on the same underlying physics. One describes the change in light, the other the change in clocks, but both reveal that time is not uniform across gravitational differences. Near extremely compact objects, the consequences become far more dramatic. Around a neutron star, the gravitational field is so intense that time near the surface passes noticeably more slowly compared with faraway observers. Near a black hole, the effect becomes extreme. To a distant observer, clocks close to the event horizon appear to slow enormously. This does not mean that time simply stops for the falling observer in their own experience. Locally, they continue to experience time normally, in the sense that their own clock keeps ticking and their thoughts proceed in sequence. But their time, compared with distant clocks, is profoundly altered by the curved geometry around the black hole. The comparison between local experience and distant description becomes one of the most striking features of relativity. This distinction matters. General relativity does not say that a person in a strong gravitational field feels their own seconds stretching out like syrup in an obvious internal way. Instead, it says that when those seconds are compared with the seconds measured elsewhere, they do not match. Time dilation is about the relation between clocks along different paths through space-time. Each clock remains locally normal to itself. The strangeness appears in comparison. That is one reason relativity can feel so subtle. It preserves local consistency while changing the large-scale structure within which comparisons are made. In a deeper sense, gravity changes time because gravity is no longer merely something happening in time. It is something woven into the geometry that gives time its meaning. The old image of time as a universal river flowing identically everywhere gives way to a more intricate world, in which duration depends on depth within gravity's landscape. Massive bodies do not just influence motion, they influence the rate at which the universe unfolds for nearby clocks. This has philosophical weight as well as scientific importance. It means that time is not a detached background before which the universe performs. It is part of the performance, part of the structure, part of what matter and energy help shape. A mountain, a planet, a star, and a black hole do not merely occupy space. They modify the temporal conditions around them. In general relativity, to exist somewhere is also to exist within a particular rate of time, and that leaves us with a quiet and astonishing thought. The pace of existence is not perfectly the same everywhere, even though daily life teaches us to imagine that it is. Time, which feels so private and inward, is also cosmically sculpted by the presence of matter. We live our lives on the surface of a world that is gently slowing time around it, and we rarely notice. Perhaps that is part of what makes the universe feel so deep. Even the passing of a moment is not separate from the shape of reality, and every ordinary second is already participating in a structure far larger than itself. Chapter 6. The Arrow of Time and Why the Past Feels Different from the Future. One of the strangest things about time is that physics often describes the world in ways that do not seem to care very much about which direction time is moving. If you watch a planet orbiting, a pendulum swinging without friction, or two billiard balls colliding in an idealized way, the basic equations can often work almost as well, whether time is imagined as moving forward or backward. And yet ordinary life does not feel like that at all. A glass falls and shatters, but the shards do not leap back up and form an intact glass. Cream disperses through coffee, but it does not spontaneously separate itself again into neat layers. We remember yesterday, but we do not remember tomorrow. The future feels open, while the past feels fixed. This one-way character of lived reality is often called the arrow of time. The most important scientific arrow of time in everyday physics is the thermodynamic arrow. It is tied to the second law of thermodynamics, which says that in an isolated system, entropy tends to increase. Entropy is a subtle concept, but in this context, it can be understood as a measure connected to how many microscopic arrangements correspond to the same large-scale condition. A tidy, highly constrained state usually corresponds to relatively few microscopic possibilities. A more spread out, disordered state usually corresponds to many more. Because there are vastly more disordered arrangements than orderly ones, systems naturally evolve from less probable macroscopic states toward more probable ones. That statistical tendency is what gives thermodynamics its direction. It is not that disorder is magically preferred by some hidden force. It is that disordered states are overwhelmingly more numerous. This is why broken cups are common and unbreaking cups are not. There is nothing in the fundamental microscopic picture that marks shattered pieces as forbidden and a whole cup as allowed. In principle, if every particle involved were arranged with absurd precision, the reverse process would not violate the basic mechanical laws. But the number of microscopic states corresponding to a shattered cup scattered across a floor is enormously larger than the number corresponding to one intact cup sitting neatly on a table. So when a cup breaks, it moves from a relatively special macroscopic condition to a vastly more probable one. The reverse would require a fantastically precise and coordinated rearrangement, so improbable that it is effectively never seen in ordinary life. That statistical character is essential. The second law is not best understood as a rigid prohibition in the style of a traffic barrier. It is a statement about overwhelming likelihood in systems with many particles. A gas released into a room spreads out because there are vastly more ways for it to occupy the whole room than to remain bunched in one corner. Heat flows from hot objects to cold ones because there are vastly more microscopic arrangements corresponding to a more even distribution of energy than to a sharply uneven one. Entropy increase is therefore not just a story about messiness in a casual sense. It is a story about probability, multiplicity, and the difference between rare macroscopic arrangements and typical ones. But this immediately raises a deeper question. If the microscopic laws are often reversible, then why does entropy increase in one time direction rather than the other? Why do we not just say that entropy increases away from the present in both directions, making the distinction between past and future somehow local or illusory? The answer leads to one of the most profound facts in modern cosmology and statistical physics. The observable arrow of time appears to depend on the universe having begun, or at least once existed, in an extraordinarily low entropy condition. The reason entropy rises toward what we call the future is that the past was very special. This is a remarkable claim because it means the everyday asymmetry between past and future may be rooted not mainly in the local objects around us, but in the large-scale condition of the universe. If the early universe had been in a generic high-entropy state, there would be no ordinary thermodynamic arrow like the one we observe. There would be no widespread formation of stars as we know them, no long chain of energy flows from hot to cold sustaining complex structure, and likely no familiar conditions for memory, biological evolution, or technological civilization. The fact that irreversible processes are everywhere suggests that the universe once occupied a state of exceptional order from the thermodynamic point of view. This can sound confusing because the early universe is often described as hot and dense. And people sometimes assume that hot and dense must automatically mean high entropy. But temperature alone does not settle the matter. In cosmology, gravity changes the story dramatically. A smooth distribution of matter can actually represent relatively low entropy when gravity is important, because gravity tends to amplify clumping, leading over time to stars, galaxies, black holes, and increasingly structured gravitational configurations. The young universe appears to have been remarkably smooth on large scales, and that smoothness is part of what makes it thermodynamically special. So the arrow of time is not just a local fact about kitchens, weather, and aging. It may be a consequence of the cosmos beginning in an unusually low entropy gravitational state. Once that low entropy past is in place, many other arrows follow. The thermodynamic arrow helps explain the psychological arrow, the reason we remember the past but not the future. Memory formation is a physical process. Brains, notebooks, photographs, fossils, and computer files are all records, and records are created by irreversible processes that increase entropy overall. A memory is not a ghostly exception to physics. It is a physical trace left by interactions in which energy is dissipated and correlations are formed. We have records of the past because the present has been causally shaped by earlier states of the world. We do not have records of the future because the future has not yet played that causal role in shaping present physical structures. In that sense, memory points backward because thermodynamics does. The same logic applies to causation in ordinary life. We feel that causes come before effects, not after them. A match ignites paper, a hand pushes a door open, a stone breaks a window. Part of this intuition comes from the way correlations build up over time as entropy increases. Earlier states help generate later records and later arrangements. Once the window is broken, many traces of that event remain in the shattered glass, the sound, the motion of the air, and perhaps in someone's memory. The reverse would require a pattern of converging influences so delicate and improbable that it is not encountered in normal macroscopic reality. Our sense that causes precede effects is therefore deeply connected to the thermodynamic asymmetry of the world we inhabit. This also helps explain why the future feels open while the past feels fixed. The past feels fixed because records of it exist in the present. They may be incomplete or misleading, but they constrain what plausibly happened. The future feels open because no such records exist yet. That does not automatically settle philosophical debates about determinism, but it does explain a large part of the asymmetry of experience. We stand amid traces of what has already occurred, while what has not yet occurred has left no comparable physical imprint. The difference between memory and anticipation is rooted not only in consciousness, but in the thermodynamic structure of the world. There is another subtle point here. Entropy increase does not mean that all forms of order simply vanish. In fact, local order can emerge and persist precisely because entropy increases overall. Life is a beautiful example. Living systems maintain and build complex structure by taking in usable energy and releasing waste heat, increasing the entropy of their surroundings in the process. The same is true of storms, stars, ecosystems, and human civilizations. The arrow of time is not merely a march toward blandness at every scale. It is the condition under which temporary pockets of complexity can arise, persist, and transform. Local structure and global entropy increase are not enemies. Quite often, the former depends on the latter. Still, the long-term implication of thermodynamics is sobering. If the universe continues evolving toward higher entropy on the largest scales, then the availability of free energy that powers organized processes will decline. Stars will not burn forever. Gradients will not remain sharp forever. The arrow of time that makes life and memory possible is also tied to the gradual consumption of the very differences that sustain them. In that sense, the arrow of time is both creative and erosive. It opens the possibility of history, but it also ensures that no arrangement lasts unchanged. Physicists continue to debate the deepest explanation of the arrow. The second law describes the direction we observe, but the question of why the past was so low in entropy remains one of the great foundational issues in science. Some see the answer in cosmological boundary conditions, some in deeper features of gravitational physics, and some in still unresolved aspects of statistical reasoning. What is broadly agreed, however, is that the asymmetry between past and future in ordinary life is not simply written into all fundamental laws in a direct way. It emerges from the interplay between microscopic reversibility, probability, and the special state of the early universe. That makes the arrow of time both familiar and astonishing. It is familiar because it appears in every cooling drink, every aging face, every fading echo, every remembered morning. It is astonishing because those everyday asymmetries may depend on conditions laid down across the whole cosmos. The reason the past feels different from the future may reach far beyond human life, beyond biology, beyond Earth itself, into the deepest history of the universe. And perhaps that is the quiet wonder beneath it all. What we call a moment passing is not just a private feeling, but part of a vast thermodynamic story stretching from the early universe into every ordinary room. We remember, change, and move forward because the cosmos itself was once arranged in a way that made history possible. The past feels different from the future because reality has been unfolding along a direction that allows traces to gather, worlds to form, and brief conscious lives to notice the difference at all. Chapter 7: Time in the Quantum World. When physics moves from the visible world of planets, clocks, and falling objects into the microscopic world of atoms, electrons, and quanta, time begins to occupy a stranger role. In classical physics, time served as a steady background against which change unfolded. In relativity, time became entangled with motion and gravity. But in ordinary quantum mechanics, time enters in a different and rather asymmetric way. Position, momentum, spin, and energy are treated as quantum observables associated with the state of a system, while time usually appears as an external parameter that tracks how that state changes. This difference is one of the reasons the quantum treatment of time feels so unusual. Quantum theory revolutionized matter and measurement, yet it did not fully revolutionize time in the same way. In the standard formulation of quantum mechanics, the state of a system evolves with time according to precise mathematical rules. The theory tells us how probabilities change, how superpositions develop, and how interactions alter possible outcomes. But time itself is usually not represented by an operator in the same sense as position or momentum. One does not typically speak of measuring a particle's time observable in the same basic way one measures its location or momentum. Instead, time is the parameter with respect to which the state evolves. This creates a conceptual imbalance at the heart of quantum theory. Matter is quantized and measurable properties are encoded in the quantum state, but time often remains classical in the formalism, as though it were supplied from outside the quantum world rather than arising within it. That does not mean time is unimportant in quantum physics. On the contrary, quantum theory is full of temporal structure. A quantum state evolves. An unstable particle survives for a while and then decays. An atom absorbs and emits radiation with characteristic frequencies. Interference patterns depend on phase evolution over time. Quantum tunneling is associated with processes that provoke deep questions about duration. But these are examples of time organizing quantum change, not necessarily of time becoming a fully symmetrical quantum variable. This is one reason physicists and philosophers have long emphasized that quantum mechanics treats time differently from many other physical quantities. The theory works extremely well, but its treatment of time is not conceptually complete in the same way its treatment of some other observables appears to be. One of the most famous features of quantum theory is superposition, the fact that a system can exist in a combination of possible states until measurement yields a definite outcome. Time enters here in a subtle way. Between measurements, the quantum state evolves smoothly and lawfully. Yet when a definite result is obtained, the language of quantum theory often shifts from continuous evolution to outcome selection. Different interpretations describe this differently, but the tension is well known. The theory gives us a rule for the development of probabilities through time, and then it gives us rules connecting those probabilities to actual measurement results. That is one reason the quantum world can feel temporally strange. It is not merely that tiny objects behave oddly. It is that the relation between continuous evolution and definite events becomes difficult to interpret. Quantum theory also changes what it means to predict the future. In classical mechanics, one could imagine, at least in principle, perfect prediction if the initial conditions were known precisely enough. In quantum mechanics, the theory usually predicts probabilities for outcomes rather than one certain future result for an individual event. This does not mean quantum theory is vague or imprecise. Its predictions are among the most accurate in all of science. But the temporal picture is different. The future is not described simply as one exact unfolding path hidden from us by ignorance. Instead, the theory offers a structured distribution of possibilities that evolves over time and yields definite statistics across repeated experiments. In this sense, time in the quantum world is linked not only to change, but to the unfolding of probabilities. There is also a famous relation between energy and time that often causes confusion. In introductory discussions, people sometimes hear that energy and time are subject to an uncertainty relation. That phrase is not wrong, but it can be misleading if it suggests that time works exactly like position in relation to momentum. The energy-time relation does not usually arise from time being an ordinary observable represented by a standard operator in the same way. Instead, it is tied to how rapidly a system changes, how long a state persists, and how precisely certain energy features can be defined over finite durations. For example, unstable quantum states that exist only briefly tend to have a broader spread in energy. This is a real and important quantum fact, but it does not place time on exactly the same formal footing as position or momentum in standard theory. At the same time, quantum physics has become one of the deepest tools humans possess for measuring time. Atomic clocks rely on quantum transitions of extraordinary regularity. The frequencies associated with atomic processes provide standards far more stable than the motions of classical devices. In that sense, the quantum world is not only conceptually puzzling about time, but practically indispensable for defining and measuring it with remarkable precision. The modern second is realized through atomic behavior, meaning that quantum phenomena now anchor humanity's most precise temporal standards. This is a beautiful contrast. Quantum theory complicates the meaning of time, yet it also gives us the finest clocks ever built. Quantum entanglement adds another layer to the picture. When parts of a system become entangled, their measurable properties can no longer be described independently in a simple way. The quantum state belongs to the whole arrangement rather than to each part separately. This does not allow signals to travel backward in time or faster than light in ordinary quantum theory, but it does force us to abandon simple classical intuitions about separated objects carrying entirely independent sets of properties. In some modern ideas, entanglement is not only a feature of quantum matter, but may be deeply connected to how space-time itself is organized. These ideas remain areas of active research rather than settled doctrine, yet they reveal how the quantum world keeps pressing against our usual temporal and spatial intuitions. The deepest difficulty appears when physicists try to combine quantum theory with general relativity. In general relativity, time is not an external background parameter. It is part of the dynamical geometry of space-time, shaped by matter and energy. But in standard quantum mechanics, time is usually supplied from outside as a fixed parameter. These two frameworks therefore treat time in very different ways. When one attempts to quantize gravity, this clash gives rise to what is often called the problem of time. Very roughly, the difficulty is that the fundamental equations in some approaches to quantum gravity do not contain time in the ordinary familiar way, even though the world we experience is full of temporal order and change. Physicists then face a profound question. If time is not fundamental in the final theory, how does the ordinary experience of time emerge at all? This is one of the reasons time in the quantum world remains unfinished science as much as established science. Ordinary quantum mechanics is extraordinarily successful in the laboratory, and it gives correct predictions across a vast domain. But when we ask what time really is at the deepest level, especially where quantum theory and gravity should meet, the answers become uncertain. Some approaches suggest that time may emerge from correlations between physical systems rather than existing as a fundamental ingredient. Others attempt to recover familiar time from semi-classical approximations, where part of the universe plays the role of an effective clock for the rest. Still others imply that our ordinary temporal language may be approximate, useful at large scales, but not ultimate. None of this means that time is an illusion in any trivial sense. It means that the role time plays in the most fundamental physics may be subtler than any earlier theory allowed. Quantum theory also complicates the idea of an event happening at one exact instant in the sharp classical sense. In many experimental settings, what physicists actually calculate are transition probabilities, amplitudes, lifetimes, and correlations over intervals. The picture is less like tiny billiard balls carrying perfectly defined properties through a perfectly defined timeline, and more like a structured mathematical framework that assigns probabilities to outcomes and tracks how those probabilities evolve. This does not remove time from the theory, but it does soften the classical image of what it means for something to happen. At the quantum level, change can be lawful without being classically picturable in every detail. That is part of the theory's power and part of its unease. Even the vacuum, which classical intuition might imagine as empty and still, is treated in quantum field theory as active in a deeper sense. Quantum fields possess fluctuations in structure, even in states of lowest energy. Particles are understood not as tiny permanent beads, but as excitations of underlying fields. Time in that setting remains essential for describing dynamics, interactions, and decay. Yet the world being described is no longer made of stable little objects evolving in the old classical way. The quantum world replaces that picture with fields, excitations, probabilities, and correlations. Time remains part of the formalism, but the things that exist in time are already far stranger than common sense expected. So what is time in the quantum world? In ordinary quantum mechanics, it is usually the parameter that orders change without itself being quantized in the standard way. In quantum clocks, it becomes measurable with astonishing precision through atomic regularity. In entanglement and measurement, it participates in processes that challenge classical notions of sequence and separability. In quantum gravity, it becomes a foundational problem, raising the possibility that familiar time may be emergent rather than basic. The result is not one single answer, but a layered scientific picture. Quantum theory did not erase time. It exposed how incomplete our understanding of time still is. There is something quietly profound in that. The deeper we look into matter, the less the universe resembles a simple machine unfolding through a universal ticking background. At the smallest scales we can describe so well, time remains both indispensable and elusive. Perhaps that is why the quantum world feels so haunting. It does not tell us that time disappears, but it does suggest that the flow we live inside may be only the surface expression of something far stranger, waiting beneath the limits of ordinary intuition. Chapter 8. Time in the Universe. When we speak about time in the universe, we are no longer talking only about clocks on Earth, human memory, or even the strange behavior of time near fast motion and strong gravity. We are speaking about time on the largest scale available to science, the history of the cosmos itself. This is a different kind of question. It asks not only how time is measured, but how time is built into the structure and evolution of the universe as a whole. In cosmology, time becomes historical. The universe has not remained the same. It has changed, cooled, expanded, formed structure, and developed layers of complexity. To understand cosmic time is to understand that the universe has a past. Modern cosmology describes the universe as evolving from a much hotter, denser early state. This does not mean that the universe expanded into empty space around it, as though it were an explosion inside a pre-existing container. Rather, space itself has been expanding, carrying galaxies apart on large scales. In that framework, cosmic time is the parameter used to describe the overall evolution of the universe under the assumption that, when averaged over sufficiently large distances, the universe is homogeneous and isotropic. That idea, often called the cosmological principle, allows cosmologists to speak meaningfully about the age of the universe and about stages in cosmic history. One of the most remarkable achievements of modern science is that the age of the universe is not a matter of myth, guesswork, or simple philosophical speculation. It is estimated from observation, especially from the expansion of the universe and from the cosmic microwave background, the ancient radiation left over from the early hot universe. Measurements from missions such as Planck and earlier work such as WMAP have shown that the universe is about 13.8 billion years old. That number is not obtained from one single clock floating somewhere in space. It is inferred by fitting observations to well-tested cosmological models. Still, the result is astonishing. Science can assign an age to the observable cosmic history with high precision. The cosmic microwave background is especially important because it gives us a snapshot of the universe when it was still very young, roughly 380,000 years after the hot beginning. Before that time, the universe was so hot and dense that light could not travel freely for long distances. Matter and radiation were tightly coupled in an opaque plasma. As the universe expanded and cooled, atoms formed, and light was finally able to travel more freely. That ancient light is still with us today, stretched by cosmic expansion into microwave wavelengths. It is the oldest light we can directly observe, and it allows cosmologists to reconstruct early conditions with extraordinary power. This point matters because cosmic time is not just an abstract axis, it is written into relics. The universe carries evidence of its own past. The microwave background tells us about the infant universe. The abundance of light elements tells us about processes in the first minutes. The large-scale distribution of galaxies tells us how structure grew over billions of years. Starlight from distant galaxies lets us look backward because light takes time to travel. In astronomy, distance is inseparable from history. To look far away is to look into the past. That is one of the most beautiful and disorienting facts in all of science. The night sky is not a single moment spread across space. It is a layered archive of different times arriving together. This also means that the observable universe has a time-defined horizon. Because the universe has a finite age and light travels at a finite speed, there is a limit to how far we can see. The observable universe is not necessarily the whole universe. It is the region from which light has had time to reach us since the early stages of cosmic history. Due to the expansion of space, the present-day size of that observable region is much larger than one might expect from simply multiplying the age of the universe by the speed of light. The observable universe extends for more than 46 billion light-years in every direction, even though the age of the universe is about 13.8 billion years. This is one of the places where everyday intuition fails and cosmology must take over. Cosmic time also gives structure to the history of matter. In the earliest moments, the universe was dominated by extreme temperatures and densities. As it expanded, it cooled. Particles formed and interacted. Light elements emerged in the early nuclear era. Much later came neutral atoms, then stars, galaxies, and eventually the heavier elements forged in stellar interiors and explosive events. Planets formed around later generations of stars. Biological history came far later still. Human history occupies a vanishingly thin layer near the recent end of a cosmic timeline that stretches back billions of years. To say that time in the universe is vast is true, but not yet enough. It is not merely long. It is staged, with different physical possibilities opening and closing as the universe changes. There is another subtlety here. When cosmologists speak of the age of the universe, they usually mean cosmic time, measured along a family of observers who move with the general expansion of the universe rather than racing through it. This is an idealized but useful notion. In a curved and evolving space-time, there is not always one simple universal time available in every possible sense. Yet in the standard cosmological model, there is a meaningful large-scale time coordinate associated with the overall evolution of the cosmos. So although relativity taught us to give up naive universal time in local physics, cosmology recovers a kind of large-scale cosmic time under specific assumptions about the universe's structure. This is not a return to old Newtonian absolute time. It is a model-based temporal framework tied to the expansion history of the universe itself. The expansion of the universe also changed our understanding of the future. For a long time, cosmologists debated whether the expansion would eventually stop, reverse, or continue forever. Observations of distant supernovae revealed something unexpected. The expansion of the universe is accelerating. That discovery transformed modern cosmology. It implied that on the largest scales, the universe is not simply coasting outward after an early beginning, but is evolving under the influence of something causing expansion to speed up. This is usually described in terms of dark energy within the standard model of cosmology, though its deeper nature remains uncertain. What matters for our topic is that cosmic time is not only about the past. It also shapes the future history of expansion, structure, isolation, and the long-term fate of galaxies. Because expansion is accelerating, distant galaxies will in the far future become increasingly inaccessible to observation from our region of the universe. Light emitted from some regions may never reach us. The cosmos is dynamic, not only in what it has already done, but in what it will permit future observers to know. In that sense, time in the universe is tied to horizons not only of sight, but of knowledge. There are parts of cosmic history we can still study because their light is reaching us now, and there are futures in which much of that evidence will fade from view for whatever observers may exist then. Cosmology is therefore historical in a double sense. It studies the universe's past, and it reminds us that the availability of the past depends on when in cosmic history one is looking. This raises one of the deepest questions of all. Did time itself begin with the hot early universe, or did something in some sense come before it? Modern physics can describe the universe back to extremely early stages with great success, but the phrase "before the Big Bang" is not straightforward. In some models, asking what happened before the beginning of cosmic expansion may be meaningful. In others, the question may fail because time, as physically defined, is tied to the universe's own history and geometry. Science has not settled this fully. What it has settled is more modest and still profound. The observable universe has a finite past that can be studied, and time in cosmology is inseparable from that evolving history. So time in the universe is not merely the ticking of better and better clocks. It is the unfolding of the cosmos from simplicity to structure, from plasma to stars, from young transparency to ancient background glow, from dense beginnings to expanding distances. Cosmic time gives order to the story of everything we can observe. It tells us that the universe has not always looked the way it does now, and it will not always look this way in the future. Even the sky above us is not a static ceiling. It is a moving historical record. There is something deeply humbling in that perspective. The universe has a history unimaginably older than human life. Yet, It is only through brief conscious beings like us that part of that history becomes known. We live in a late chapter of a cosmic process vast enough to form galaxies and subtle enough to preserve ancient light across billions of years. And still, for a little while, the universe has become able to look back across time and notice that it has been changing all along. Chapter 9. Can time end, loop, or break? By the time we reach the far edges of modern physics, time stops looking like a single smooth idea. In ordinary life, time seems to move forward in one direction, carrying events from possibility into memory. In relativity, time becomes tied to motion and gravity. In thermodynamics, it acquires an arrow through entropy. In quantum theory, it becomes conceptually unstable in a different way. Sometimes treated as a background parameter, sometimes as part of a deeper unsolved problem. So it is natural to ask whether time can do something even stranger. Can it come to an end? Can it bend back on itself? Can it fail altogether as a meaningful part of reality? One place where this question becomes unavoidable is the black hole. General relativity predicts that if enough mass collapses into a sufficiently small region, space-time becomes so strongly curved that an event horizon forms. Beyond that boundary, escape to the outside world is no longer possible. According to the classical theory, continued collapse leads to a singularity, a region where the mathematical description provided by general relativity breaks down. Physicists often say that density becomes infinite there, but the deeper point is that the theory itself no longer gives a physically adequate description. A singularity is not merely an exotic object sitting somewhere in space and time like an ordinary thing. It marks a limit of the theory, a place where the known structure of space-time can no longer be extended in the usual way. That breakdown matters because it suggests one sense in which time may end. In certain solutions of general relativity, time-like paths cannot be extended indefinitely. An observer falling inward may encounter a boundary beyond which the classical notion of continued passage through space-time ceases to be defined by the theory. This does not mean that a clock literally reaches a sign reading "time stops here." It means that the theoretical framework runs out. If the equations imply a singular edge to a time-like world line, then classical space-time is incomplete there. In that technical sense, time can end, not because the universe suddenly chooses to pause, but because the geometry described by general relativity no longer supports an ordinary continuation. A similar issue appears when cosmologists discuss the beginning of the universe. In the standard cosmological model, the observable universe evolves from an early hot, dense state. If the equations of classical general relativity are pushed backward far enough under certain assumptions, they point toward an initial singularity. Once again, the safest scientific reading is not that physics has perfectly described a literal first instant beyond all doubt. The safer conclusion is that classical relativity, when extrapolated backward, reaches a regime where curvature and density become extreme, and the theory no longer suffices. So if time had a beginning in the classical picture, that beginning may actually be telling us that a deeper theory is needed. In both black hole singularities and the earliest universe, the question is not merely what happened there, but whether classical time remains meaningful there at all. This is one way time may break. Not by shattering like glass, but by reaching the boundary of a theory. General relativity is one of the most successful scientific frameworks ever built. yet it appears to predict its own incompleteness in some extreme circumstances. That is one reason so much hope has been placed in quantum gravity. Physicists expect that a more fundamental theory, somehow combining quantum principles with dynamical space-time, may replace classical singularities with something better behaved. But as of now, there is no complete and experimentally confirmed theory of quantum gravity. So the idea that time breaks at singularities remains both scientifically serious and scientifically unfinished. A different possibility is that time does not end, but loops. General relativity allows solutions in which space-time contains closed, time-like curves. A time-like curve is the sort of path that a material object moving slower than light could in principle follow. If such a curve closes back on itself, then an object traveling along it could, in a sense, return to its own past. This is the rigorous relativistic root of what is commonly called time travel. It is not merely a literary fantasy imposed from outside physics. Certain space-time geometries permitted by Einstein's equations do contain structures of this kind. That statement needs caution. To say that closed time-like curves are allowed by some solutions of general relativity is not the same as saying they exist in the real universe or can be built by advanced engineering. Some famous examples, such as Gödel's rotating universe, are mathematically consistent but do not resemble the observed cosmos. Other proposals involving wormholes or specially arranged distributions of matter and energy raise severe physical difficulties. The equations of general relativity are generous in what they permit mathematically, but nature may be far stricter in what it actually allows. Closed time-like curves are especially troubling because they appear to invite paradoxes. The familiar example is the grandfather paradox, in which a traveler goes to the past and prevents the conditions required for the trip itself. Physicists and philosophers have offered various responses. One approach is self-consistency. Perhaps events on a closed time-like curve must fit together in a globally consistent way, so paradoxical actions are never actually realized. Another approach is chronology protection, associated with Stephen Hawking, which suggests that the laws of physics may prevent the formation of closed time-like curves under realistic conditions. There is still no universally accepted final answer, but the important scientific point is that time loops are not simple nonsense. They arise from serious examination of relativistic spacetime, even if the universe may ultimately forbid them. The possibility of loops also forces us to think carefully about causation. In ordinary life, causes seem to precede effects in a clean forward order. But on a closed time-like curve, causal structure can become circular. An event may help bring about conditions that are themselves part of its own past. This does not necessarily violate the local laws of physics, but it strains deeply held intuitions about explanation. Instead of a straight chain, causation becomes a loop. That is one reason time loops feel so disturbing. They challenge not only chronology, but the very structure by which we normally understand why things happen. There is yet another sense in which time may fail, and it comes not from loops or singularities, but from attempts to describe the deepest level of reality. In some approaches to quantum gravity, the ordinary idea of time does not appear in the fundamental equations in the familiar way. This is sometimes called the problem of time. In general relativity, space-time geometry is dynamical rather than fixed. In ordinary quantum mechanics, time is usually treated as an external parameter. When physicists try to combine the two frameworks, The result can be a description in which familiar temporal evolution is no longer straightforwardly present. This raises a startling possibility. Perhaps time as we experience it is not fundamental, but emergent. Emergent does not mean unreal in the cheap sense. Temperature is emergent from molecular motion, yet it is a real and measurable feature of the world. Likewise, if time is emergent, that would mean it arises from deeper non-temporal or differently structured relations at a more fundamental level. Some physicists explore the idea that temporal order comes from correlations between parts of the universe, rather than from an independent master clock. Others investigate frameworks in which causal structure is more basic than ordinary continuous time. None of these proposals is settled science in the way that atomic physics or general relativity within their tested domains are settled, but they show that at the frontier of fundamental theory, can time break becomes almost synonymous with was time ever fundamental in the first place. It is important not to overstate the speculative parts. There is no confirmed evidence that macroscopic time loops exist. There is no finished theory proving that time disappears at the deepest level. There is no laboratory result showing that human beings could step outside chronology. The strongest claims here are more limited and more scientific. General relativity permits exotic geometries, including some with closed time-like curves. Classical relativity predicts singularities under certain conditions, which likely signal its incompleteness. Quantum gravity remains unfinished, and one of its major conceptual difficulties concerns the status of time itself. Those statements are solid. The rest remains an open frontier. So can time end, loop, or break? According to our best current physics, each possibility appears in at least one serious sense. Time can end in the limited but important sense that classical spacetime may be geodesically incomplete at singularities. Time can loop in certain solutions of general relativity that contain closed time-like curves, though whether nature allows them is unresolved. Time can break in the sense that our deepest existing theories cease to give a complete account under extreme conditions, and in the further sense that time itself may not survive unchanged in a more fundamental quantum gravitational description. These are not casual metaphors. They are signs that the temporal order we live inside, though reliable at human scale, may not be the final layer of reality. And perhaps that is the quiet strangeness at the edge of this chapter. Time feels like the most faithful thing in our lives, the medium through which everything else changes. Yet at the limits of physics, even time may have boundaries, twists, or hidden depth. We live by minutes and years as though they were simple, while the universe may hold regions where chronology curls back, dissolves, or gives way to something more profound than duration itself. Chapter 10. Living Inside Time. After all the abstractions of physics, there is still a simpler fact that never leaves us. Human beings do not merely study time, we live inside it. We wake, age, anticipate, remember, wait, recover, and decay within processes that unfold across seconds, days, seasons, and years. Even when physics reveals that time is not absolute, not universal in the old classical sense, and perhaps not even fundamental at the deepest level, daily life continues to be shaped by temporal order. Bodies follow rhythms. Minds organize experience into before and after. Memories accumulate. Organisms develop, mature, and decline. To live at all is to participate in time as an active biological and psychological condition. not just as an abstract coordinate in a scientific theory. One of the clearest ways we live inside time is through biological rhythm. Human beings are not temporally neutral creatures drifting through identical hours. We are organisms with circadian rhythms, recurring cycles of physical, mental, and behavioral change that are strongly shaped by the daily pattern of light and darkness. These rhythms influence sleep and wakefulness, alertness, hormone release, metabolism, and many other processes. The body does not experience morning, afternoon, and night as interchangeable blocks. They are biologically distinct conditions. This means that lived time is partly written into physiology. A day is not simply a measure on a clock. It is a cycle in which the body repeatedly reorganizes itself. This is one reason disrupted sleep can make time feel strange. When circadian rhythms are misaligned, whether through shift work, jet lag, irregular light exposure, or chronic sleep disturbance, people often report that days blur, nights lose structure, and attention becomes unstable. The world still turns, but the body's internal timing no longer fits comfortably with the external environment. Living inside time, therefore, means more than being aware of clocks. It means being synchronized, however imperfectly, with recurrent biological patterns that developed over evolutionary history under the cycle of day and night. We also live inside time through memory. A human life is not experienced as a disconnected set of isolated instants. It is held together by the ability to retain traces of what has happened and to organize those traces into a personal past. Memory is not merely a storage box containing snapshots. It is part of how identity persists. Philosophical and scientific discussions of memory both emphasize that memory underwrites our knowledge of the past and our sense of continuity as individuals. Without memory, there would still be biological life, but the narrative form of human existence would be profoundly damaged. In that sense, living inside time means carrying earlier moments forward within the present. At the same time, memory is selective and reconstructive. The past is not preserved in the mind with perfect neutrality. It is reorganized, compressed, emotionally colored, and sometimes distorted. This matters because our sense of time is partly built from what memory preserves and what it lets fade. Certain years feel long in retrospect because they are rich in memorable change. Other stretches seem to collapse because routine leaves fewer distinct traces behind. The result is that human time is not only chronological, it is textured by significance. Two equal calendar intervals can feel profoundly unequal when recalled from later life. Attention shapes lived time as well. Psychology has long observed that duration feels different depending on whether attention is focused on passing time itself or absorbed in activity. Intervals often seem longer when one is waiting and shorter when deeply engaged. The human experience of time is therefore not just something that happens to us from outside. It is partly generated by how the mind distributes awareness. This is one reason a day can feel slow while it is being endured, yet brief when remembered later, or full while it is unfolding, yet strangely compressed in memory. Living inside time means inhabiting this shifting relation between attention, duration, and recollection. Then there is aging, perhaps the most intimate long-term expression of temporal life. A stone can erode and a star can exhaust its fuel. But an organism's aging carries an especially personal meaning because the organism is not merely changing physically. It is also the subject experiencing that change. Modern biology describes aging through a set of interacting molecular and cellular processes, including genomic instability, epigenetic alteration, mitochondrial dysfunction, cellular senescence, stem cell exhaustion, and altered intercellular communication. These are not poetic metaphors. They are research-grounded descriptions of how biological systems lose resilience over time. Aging is therefore not simply the passage of time in a vague sense. It is the cumulative transformation of living matter under the constraints of metabolism, repair, stress, and history. Yet aging is not only decline, it is also development. A human being does not begin life as a finished state and then merely deteriorate. Life unfolds through stages of growth, learning, reproduction, adaptation, and only later increased vulnerability. Living inside time means being shaped by irreversible processes at many scales, from embryonic development to the consolidation of skill, from social maturity to biological aging. The body changes because it is alive, not because it has somehow failed to resist time. Time is the medium through which living systems become what they are. This brings us to a quieter point. Human beings are temporal creatures, not only because they change, but because they project themselves forward. We plan, fear, hope, delay, and imagine. A large part of ordinary consciousness is future-oriented. Even rest is often postponed in thought by what still needs to be done tomorrow. Philosophical work on temporal experience notes that consciousness is not merely located in time, but is itself permeated by temporality, by awareness of succession, persistence, and becoming. We do not simply register events one by one like a machine stamping tickets. We inhabit a moving horizon in which the just past lingers, the present is experienced as flowing, and the near future is continually anticipated. This is why time can feel heavy. To live inside time is to know that moments do not merely exist, they pass. Biological systems age, opportunities close, wounds heal or fail to heal, habits strengthen, and relationships deepen or end. The same temporality that makes growth possible also makes loss unavoidable. But this is not only a human sadness layered onto neutral physics. It is part of what temporal existence is. A world without change would not contain aging, but it would not contain learning, healing, or becoming either. Duration allows both erosion and formation. There is something else worth noticing. Although physics can describe time in impersonal ways, living inside time always has a scale. Human beings do not feel billions of years directly. We feel sleepless nights, long afternoons, birthdays, recovery periods, grief that softens slowly, and routines that quietly become years. Cosmic time and relativistic time are real, but lived time is often measured in pulses of embodiment and memory. This does not make human time less scientific. It means that biology and cognition are themselves part of nature, and therefore part of the full scientific story. The universe does not stop being physical when it becomes personal. In that light, clocks are both powerful and limited. They measure intervals with extraordinary precision, especially in the modern atomic age. But they do not capture the whole reality of living through a day. A clock can tell us how long we slept, yet not how restored we feel. It can mark a year, yet not what that year meant. It can count lifespan, yet not contain a life. Scientific accuracy matters, but so does the recognition that human temporality includes physiology, memory, attention, and identity. To live inside time is to stand where physical duration and conscious experience meet. So the final lesson of this journey may be the simplest one. Time is not only out there in space-time, black holes, or the early universe. It is also here, in the body that gets tired at night, in the memory that holds old voices, in the cells that repair imperfectly, and in the quiet fact that experience arrives in sequence rather than all at once. We are finite organisms whose knowledge, rhythms, and identities are built from temporal processes. We do not watch time from outside. We are one of the ways time becomes conscious of itself, and perhaps that is the gentle thought to end on. To live inside time is not only to be carried toward endings, but also to be given duration enough for memory, connection, and awareness. The universe does not grant permanence, but it does grant passage. And within that passage, there is room for a life to unfold, to notice, and for a little while to mean something. And now, my friend, as this journey through time comes to an end, I hope your mind feels a little quieter and your thoughts a little lighter. If you're still awake, you can stay with me and choose another video for the night. But if sleep is already finding you, then I wish you sweet dreams among the stars.